Hi all. Today we are going to look at the normal incidence of plane electromagnetic wave in a dielectric boundary. Okay, so basically you have a boundary which is separating two mediums, which is having permittivity epsilon 1 and epsilon 2, and the permeability mu 1 and mu 2 respectively. Okay, and the wave is incidenting in the z direction, and the boundary is along the x direction, so that the angle of incidence is 90 degree, or it is a normal incidence of the plane wave. Okay, so when you have such a electromagnetic wave incidenting on the boundary, it is having electric and the magnetic field components. Okay, so incident wave will be having an electric component in the x direction. Suppose it is, we assume that the electric field is polarized along the x direction, and the magnetic field is in the, obviously it will be perpendicular to the propagation direction as well as the electric field, so it should be in the y direction. Okay, and when such a wave is incidenting on the boundary, what happens is a part of the wave will be transmitted to the medium 2, and a part of the wave will be reflected depending upon the nature of the boundary or the nature of the second medium. Okay, so let's look into the problem in detail. We have in the last few lectures we have defined how to calculate the magnetic field associated with a plane wave, a plane electromagnetic wave, when the electric field is given. Okay, so we suppose that the electric field of the incident light is polarized along x direction, and it is having an amplitude ei0. Okay. Now from this relation you can actually find out the magnetic field. You just substitute this expression here, and this an is the unit vector normal to the boundary. So in this case that normal vector is in the z direction, so it is a z cap basically. So you will get magnetic field which is in the y direction. So this is the incident wave electric and magnetic field. Now as I mentioned earlier, on at the boundary separating the two medium, when the wave is incidenting on the boundary, a part of the wave will be reflected, and the reflected wave can be written as like this, because the reflected wave will be having a component in the x direction. So for denoting the amplitude of the reflected wave I am using ER0. Okay, and the reflected wave is having a phase constant beta 1 z. So this is in the still in the medium 1, and which is the magnetic field of the reflected wave is found by substituting this expression. Now the propagation direction is in the negative z direction, and you have to substitute what is ER here, and eta 1 is the intrinsic impedance of the medium 1. Okay, so if you take the cross product you will get this expression, and from this expression you know that the wave is propagating in the negative z direction. Okay, negative z direction, and it is polarized in the negative y direction. Okay, then in the medium 2 you will be having a transmitted wave. Similarly you can find out the transmitted wave here. So ET0 represents the amplitude of the transmitted wave at z equals 0, and it will be propagating in the positive z direction, and the phase constant will be beta 2 since it is in the medium 2. And similarly you can use the same expression to find out the magnetic field of the transmitted wave, and here you take the normal vector as AZ. It is propagating in the positive z direction, and substitute the value of electric field here, and eta 2 represents the intrinsic impedance of the second medium. Okay, so now you can apply the boundary conditions here. Boundary conditions, what is the boundary conditions to be satisfied by the electric and magnetic fields. Okay, basically the tangential component of the electric and magnetic field will be continuous across the boundary. So since this is the boundary, okay, that is in the x direction, the tangential component of the field will be ER, and so this all these components will be the tangential component or which is parallel to the boundary, and it should be continuous, and also magnetic field should be continuous if there is no surface current, and in our case there is no surface current. So the magnetic field tangential component of the magnetic field also should be continuous. Okay, so from that boundary conditions, okay, you can derive these expressions. What you have to do is you write down the total electric field in medium 1. So in medium 1 you will be having incident electric field and a reflected electric field. Okay, basically using these two expressions, and what you have to do is at the boundary, that is at z equal to 0, you have to substitute z equal to 0 here, z equal to 0 here, that value should be added, and that total value should be equal to the value of the tangential field at z equal to 0. So the tangential field is given by this expression. Okay, now now you can substitute the value z equal to 0 in these expressions, and you can write the amplitude relations like this: EI0 plus ER0 equal to ET0. Similarly, you can do the same steps for the magnetic field intensities. Okay, and the tangential component of magnetic field intensities also should be continuous, and from that you can arrive at this expression. Okay, so here eta 1 is the intrinsic impedance of medium 1, and eta 2 is the intrinsic impedance of the medium 2, and basically you can play around these variables and find out an expression for ER0 and ET0, that is the amplitude of the reflected wave and transmitted wave at z equal to 0 in terms of the incident electric field amplitude. Okay, so basically you can derive this expression. What you have to do is you just add these two equations and simplify, and you can also subtract this equation to obtain ET0. Okay, now you can define two parameters. One is ER0 by EI0, that is the reflection coefficient, and another parameter ET0 by EI0, that is the transmission coefficient of the medium. Okay, so if you that expression you can actually get it from this equation. You just divide ER0 by EI0. Okay, then the reflection coefficient is given by eta 2 minus eta 1 by eta 2 plus eta 1. Okay, in terms of the intrinsic impedances of the medium, and the transmission coefficient is given by this expression 2 eta 2 by eta 2 plus eta 1. If you carefully look at this expression, you can see that gamma, the reflection coefficient, can be positive or negative depending upon the value of eta 2 and eta 1. Okay, it can be negative also, it can be positive also, but the transmission coefficient, which will be always positive, because eta 2 and eta 1 are always positive. Okay, now you can also derive one expression which is connecting the reflection coefficient and transmission coefficient, which is 1 plus gamma equal to tau. Okay, now you consider the special cases. If the medium 2 is a perfect conductor, you know, for a perfect conductor intrinsic impedance will be 0, so eta 2 will be 0. Second medium is perfect conductor. Now what happens is, if you have a perfect conductor, the reflection coefficient will be -1 and transmission coefficient will be 0. Okay, you just need to substitute eta 2 is equal to 0 in these expressions. Okay, now what do you mean by this? Reflection coefficient is -1 means ER0 equal to minus EI0. So the total wave incidenting on the boundary will be completely reflected back into the medium 1, and there is no transmission amplitude, or there is the wave is not transmitted at all. Okay, if the second medium is perfect conductor. Now there is a second case which is if the medium 2 is not a perfect conductor. What you can do is you can sum up the incident wave and reflected wave in medium 1, and you just substitute it here, and you know the relation for ER0. ER0 will be gamma times EI0, so that you can substitute here, and you can play around and simplify this expression in this form. From this you can actually find out the locations of maxima and minima. Okay, and so you do this as a homework. It is simple actually. So you have some complex number here, you find out the maximum and minimum of the complex number. Okay, so remember, this is also a complex quantity and this is also a complex quantity. You have to simplify this expression. Okay, and while simplifying, you take gamma greater than 0, and the maximum value of E10, that is the modulus of electric field in the medium 1, is occurs at the points z max equal to n pi by beta 1. Okay, so that you can actually write it as n pi by n lambda by 2, where n equal to 0, 1 and 2. Lambda 1 is the wavelength, and the minimum value of z occurs at these points minus 2n plus 1 lambda 1 by 4, where n equal to 0, 1, 2, etc. Why it is negative? Negative sign indicates that it is in the they are the positions in the medium 1. Okay, so the positive side is in the medium 2 actually. Okay, now suppose gamma is less than 0, that means eta 2 is less than eta 1, then the maximum value of E10 is EI0 1 minus gamma, which occurs at z minimum, which is the minimum value of E1 z will be EI0 1 plus gamma, which occurs at z max given in equation 145, which is this, the minimum value occurs at this point, and the maximum value occurs at this point. So these positions are interchanged when you have a gamma less than 0. Now you can also define another parameter which is called standing wave ratio. So which is the ratio of maximum value to the minimum value of electric field intensity in the of a standing wave. Okay, so by this calculation you get a maximum value and minimum value of E1Z, and take up the ratio of maximum to minimum. So that will give you 1 plus modulus of gamma divided by 1 minus modulus of gamma, which is the standing wave ratio. So standing wave ratio is usually expressed in terms of the logarithmic scale. So we can define a standing wave ratio in decimal as 20 log 10 s. Okay, so the standing wave ratio ranges from 1 to infinity when gamma ranges from minus 1 to plus 1. Okay, now using these expressions, you can write down the magnetic field intensity in medium 1 obtained by combining H incident and HR reflected component of the magnetic intensity. So you can write down the magnetic field in medium 1 like this, and so these are all just combining these equations in medium 1. So we already wrote the total electric field in medium 1. Okay, and now in this expression we write down the total magnetic field intensity in medium 1. Okay, so what you have to do is you sum up the magnetic field intensity of medium 1 and incident magnetic field intensity in medium 1 and the reflected magnetic field intensity in medium 1. Okay, so then you will get a H1 of Z. So in the medium 2 you don't have incident wave, there is only transmitted wave present. So the total electric field in medium 2 is given by this expression, where tau is the transmission coefficient. Okay, and similarly you can find out the magnetic field intensity in medium 2 which is given by this expression. So this is all about the normal incidence at a plane dielectric boundary. So we have discussed the total electric field in medium 1 and medium 2, and also the magnetic field intensity is in two mediums in terms of intrinsic impedance and the propagation direction. We also defined some of the parameters like standing wave ratio and also the reflection and transmission coefficient. Okay. Now, we discuss one problem which is given in this statement. A uniform plane wave in a lossless medium with intrinsic impedance eta 1 is incident normally onto a lossless medium with intrinsic impedance eta 2. So, there is a plane wave incidenting on a medium 1 to medium 2 which are lossless, and what we have to obtain is the expression for time average power densities in both medium. So, I have already given an assignment to derive the Poynting's vector and time average Poynting's vector expression. Hope you have did that, and we have to use that equation. So, the average power time average Poynting's vector or average power transferred by the electromagnetic wave is given by this expression 1 by half real part of E cross H star. H star is the complex conjugate. Okay. And all these quantities are in the phasor notation. So, what you have to do is just need to substitute for E1 here in terms of E and H1 here in terms of H1. Okay. So, you have H1 here in the previous expression and E1 is also here. Okay. Now, you can calculate. So, if you are calculating in for the medium 1, you substitute E1 and H1. So, if you are substituting for medium 2, you have to substitute ET and HT. Okay. Now, all the steps are given here. You work out these steps, okay, and finally you will get this expression. And here one important factor is we already mentioned in the question that the medium is lossless. So, all the power which is flowing in medium 1 will be transferred to medium 2. So, the power flow in medium 1 will be equal to medium 2 also. So, let us check that. So, what you have to do is you have to again calculate P average for medium 2 and see whether they are equal. Okay. So, in medium 2 you will get some expression like this. So, which will be same as the expression for power in medium 1 because you can use this identity to connect the two equations. Okay. So, hope you understood the video. Thank you.